going to look at simple harmonic motion and damped harmonic motion. So looking at simple harmonic motion, we've got our equation here. And the solution to that is x is a sine omega t plus b. And we've got omega as the angular velocity, and we've got the period 2 pi over omega, and then we've got a as the amplitude. So let's look at plotting that. So I've got an xy grid at the moment, and I want an xt grid. And if I just drag that over there, and if I edit my axes, I'm just going to change my labels as t is in seconds and displacement is x is in meters. So if I just add that in, and then if I put in my equation, which is x double dot, so that would be x quotation marks plus omega squared, so I'm going to do w squared is equal to 0. And then we need an initial starting point. So if we say t is 0, x is 3, then we can see we've got a sine curve. And if I select that and use the text box, just so to display the equation, we can see that the omega is starting off as 1. And then using the constant controller, I want to change my omega value. If I increase it, then our period will get smaller. So if I increase that, let's see what happens. So we can see the period is getting smaller. Okay, let's now have a look at the damped harmonic motion, which has got this extra term in here. This is a velocity term. So it's a constant, which I call 2a times the x dot, the velocity. So if I look at the discriminant for this equation, so we've got b squared, which is my 2a squared, minus 4ac, which is 4 omega squared. And we've got 3 situations. So we've got where the discriminant is 0. So this is critical damping, where the particle returns to its equilibrium position in the shortest time. We've got light damping with a discriminant less than 0. So that's where the particle continues to oscillate, but the oscillations get smaller. And then we've got heavy damping where the discriminant is positive. And this is where it doesn't oscillate at all, but returns slowly to the equilibrium position. So let's have a look at that equation. So we've got x double dot plus 2a x dot, which is x apostrophe, plus omega squared x is equal to 0. And again, if we have 0, 3 as our starting position, and then I'm going to use my text box to display that equation. So I'll just take away equation 1, so I've got less on the screen. And that's my equation. I'm also going to put in the discriminant, which is 4a squared minus omega squared. And then I'm using the text box to display that one as well. So I can change that to discriminant rather than equation 2. And then OK. So let's have a look at the different cases for A and omega. Now I'm going to keep omega fixed. Omega is our angular velocity, and I'm going to change my A value. So I'm going to start off by looking at where A is a negative value. So if I do negative 1, now it's difficult to see that what's happening, but if I zoom in a little bit, I should be able to see that I've got oscillations which get bigger and bigger. So I'm just going to make my A slightly smaller so we can see that. Now I think we can see now the oscillations continue and they actually get bigger and bigger. So if I zoom back or if I zoom out again and change my A value. Now let's look at where A is 0. and that would be simple harmonic motion because the velocity term disappears. So that's where my A is equal to 0. So now let's have a look at the case where A is positive, but less than omega. So we've still got a discriminant that will be negative, and let's see what happens there. So we can see it's still oscillating, but the oscillations are getting smaller and smaller. And this might be a case where we've got, say, a saloon bar doors, where somebody comes through the doors and they continue to oscillate or flip backwards and forwards until they come back to their equilibrium. So I'm going to attach that object to the point, and then if I move, hopefully I can move that along. There we go. And there we can see it oscillating. Okay, so that's our first case. Now the second case is where we've got, or the next case rather, is where we've got the discriminant is equal to 0. So we've got A is equal to omega. So I'll change A to 1. And this is where we've got critical damping. So this would be a case, say, of this suspension in a car. So if the car goes over some bumps, we want it to go back to its equilibrium position as quickly as possible. So we've got the car attached to there, so going back to its equilibrium position as quickly as possible. Now the last case is where we've got the discriminant is positive, so our A value is bigger than the omega value. So let's see what happens there. So this is a case where we've got heavy damping, and we can see that it doesn't oscillate and it's taking a little bit longer to get back to the equilibrium position. And this might be the case of some swing doors in an office. So when somebody goes through them, we want the door to slowly move back to its equilibrium position. So if I can attach that to the point, or attach the image to the point, and let's see if we can get that to move along there. There we go. So the door is slowly going back to its equilibrium position.